Hello, friends. Welcome to the fourth and final session of the machine learning track at Global Hack Week December. Hello, hello. Oh, Polar Void actually made it. Stuart made it. Mo the Techie made it. Yes, yeah. Okay, so I guess this is the obvious thing that is pretty apparent, is that there was a tie. And so I do have a Christmas tree on this side of my face. And I am actually pretty dang proud of my blahage on this side of the face. Unfortunately, if I'm looking straight at the camera, you can kind of only barely see both of them, but I'll regularly turn from side to side. Hua, hua, hua. But we have a lot of fun stuff to do today. I actually really like, for folks that have been to more than one of these, we sort of have a cadence where, you know, like the first day we always do reintroduction to Python. The second day we always sort of like learn more about our project. The third day we build kind of a simple model. And the fourth day kind of ends up being a grab bag. Yeah, I'll just talk actually like this. Why don't I just do that? But so we have a grab bag of things today. We are going to improve our model, which is going to be a lot of fun. We're also going to announce our raffle winners. We are going to obviously admire these guys. I have some art to show you. And I think maybe we'll even spend a little bit of time talking about, because the folks who have made it to this session are like the core squad, talking about how it went and if you have any feedback for next Global Hack Week, if there's anything else you want to see. Oh, Samrid, it's been a hot minute. It's so good to see you back as well. Josh, welcome, welcome. Let's see, Mo, Barid, I think maybe. Yes, I will drop all the links. Fancy Appleby is not here today, and so unfortunately, they will not be able to drop all the links for us. But no worries. Here is the check-in for part 4. And then I am going to juggle around some windows real quick. And, okay, Barid, I don't know, It's so tricky reading usernames, but please let me know if I can fix the pronunciation of what I just said. Right on. So, oh yeah, I was going to juggle windows around and give you the link to, you already have the link to check in. I'm going to drop again the link to the notebook that we're going to be using, and it's actually going to be the same one as last time. We're going to kind of build on top of that, if this is the right link. Yes, it looks like it is. So I will share a link with y'all. Barid. Cool. Oh, there's the link that we'll be using today. I'm going to make my face bigger as well. I don't like the border. Somebody else in Global Hack Week must like the border, but we'll just keep going back and forth and swapping. There we go. I'm big now. I have to remember to keep my face looking like that, because the Christmas tree is good. It's fine. It looks like a Christmas tree, but I'm really quite proud of that. Okay, cool. So where did we leave things? We had built a really pretty simple model to take our spectrogram in and return to us predictions for all 8 of our potential sort of keywords that we were tracking. And we talked about how we wanted to maybe beef it up. We talked about how, because we were using a dense layer, in fact, I'll actually pull up I'll just get the notebook live here so I can gesture at it as I'm talking. Boom. So we talked about how we use this dense layer. And this dense layer was really connecting all of the data together. Yes. Oh yeah. This is the data. This is the machine learning track, which is different from the data science track, even though they are topics that definitely have some overlap. And I will confess that this session is probably the hardest session to jump in on if you have not been with us for the past 3 ones. Really, all of the other 3 ones you can jump in if you want to, but this one is a little bit buildy. So we talked about how this dense layer was one that took, actually, the fact that you asked that question reminds me that I did not actually introduce myself and introduce the course. So, hi, my name is Will. I'm a coach at Major League Hacking. I am a software engineer at Google. I am mildly caffeinated today, not that actually caffeinated. I have forgotten to put on my flower crown, but I'm very excited to bring us home on this journey of machine learning with sound today. So, yesterday, we were building this model, and we basically had set up sort of the simplest version of a model we could think of. They just took in our input data, flattened it just to a single layer of data, and then we used this dense network, or this dense layer. And I think Polar Void had a really, really good sort of catchphrase on it, which is the idea that this dense layer is kind of like conspiracy theory brain. It will look for connections everywhere. And so, we looked at how this spectrogram, really we can see an S shape here, and we can see a T shape here, we can see an O shape that's a little bit lower and longer, and then we can see our P shape over here. But the conspiracy theory brain, that dense layer, is going to look for connections everywhere. It's going to see, well, maybe this beginning of the S is like really connected to this just total silence over here. And that's not really actually all that helpful for us. Yes, I will. Oh, yeah, I will share my LinkedIn. Yes, my LinkedIn is, let's see, what is my LinkedIn? Oh, catch me accidentally typing in Hebrew up here. LinkedIn. If we go here, boom. That is my LinkedIn. So it's like conspiracy theory brain. It's a good way of describing it. It's going to look for connections everywhere. Oh, thank you for the kind comment on my hat. And that's not actually that helpful to us, because really, as you are listening to audio, you're really listening to it through time. And you actually compare, really, the reason that we're able to pick this out as a SA is really because it happens all connected in time, and our ears are able to stitch it together in steps as we go, right? And so looking for connections between data from over here and all the way over here, it's not that that's going to like totally destroy our model. In fact, our model got decent accuracy, but it's just not going to be as good as it could be. So something I'm going to have us do actually is today, because we're actually going to be training a slightly larger model, I want to get us an accelerator. So we have talked a lot about how to make our algorithms faster, and we spent a whole day talking about NumPy, and the whole idea of NumPy is it stores all our numbers really close together so we can do math on them really fast. Yes, we talked about tensors even. Arrays, matrices, tensors, choose your fighter. And one of the reasons that they are actually really, really powerful is because they can be loaded into accelerators really easily. Accelerators, generally, we're talking about GPUs, and also we'll put TPUs in that category. But GPUs originally created, of course, to do graphical processing, really to render the graphics on video games and in sort of video processing. But because the things you have to do video processing and rendering video games is multiply a bunch of matrices together, it makes them actually really suited to run these sort of matrix multiplications really, really quickly. And so if you come up here to this RAM disk button right here, you can actually change your run type. And we're doing this at the very beginning because it'll throw out your old run type. So all your old variables will get thrown in the garbage. And we can come over here and pick GPU. And okay, Polar Void, you were actually the person that I think like many Global Hack Weeks ago called me out on I wasn't actually using it right, but I believe I actually did change it, or that there is an update now, so that by default, if there is a GPU available that TensorFlow can find, it will use it, I think, because I was just playing around with it. And we'll use the standard GPU, and that's fine, and we'll hit save. And so this now throws away our old runtime, and so this actually asks you, do you want to throw away your previous runtime? And we'll say yes. And so now we'll come down here and we will just before, we'll come down to where we say model compile, and we can say runtime run before. So this will just automatically run all of the cells before us. So this will do sort of all of our setup work from beforehand. It's installing things for us. It is seeding it. We're pulling in our data, et cetera, et cetera. Summer says, makes me think of particle accelerators for no reason. Yeah, I mean, they make things go fast, right? That is, I guess, the through line is they accelerate things. But I suppose also, actually, you probably use computational accelerators to do a bunch of math that you need to do the physics for particle accelerators. So lots of connections. But that's me having conspiracy theory brain, I suppose. Okay, so we're going to run this, and hopefully we will get down to this point where we have created our model, and that will be happy. I was playing around, and I actually was testing this out with both running the model with your CPU and then running your model with the GPU. And if you run it without anything, it actually performed at the GPU performance. So we're just going to kind of skip all that. And I don't think we actually need this. But so we have our simple model that is just taking in our spectrogram here. Oh, we got rid of our spectrogram, didn't we? Bummer. Okay, well, it's running. We'll give it a minute. And in fact, actually, this is a great reminder for me to have a cough drop. So we're going to try to beef up our model with some convolutions. We're going to evaluate it and calculate some accuracy. We're going to plot a confusion matrix, which we'll talk about more in a second. And I think if we have time and energy, we're actually going to maybe try to supply weights for our different classes, if we feel like it. Okay, we've got our waveforms back. So our model right now is just taking basically this image. You can think of about it like an image. Yes, the recurve is so important. And so this is a 124 by 129 pixel image, basically, in grayscale. And when we compile our model, and if we run it, and let's say, I think we said 10 epochs. Well, let's go 20 epochs and see how far, like how good of performance we can get. Oh, and I feel like we plotted performance too. Did we plot performance? Or was that just in my memory? If we did not plot performance, we're going to do it today. Okay, so it's taken like 25 seconds, which honestly feels kind of long. I guess we're seeing some variability. Then we're getting a whole epoch in 9 seconds. So remember, each of these epochs is basically, we've given it a study guide, and every time it studies through the entire study guide, that's one epoch. And so you can see it even gives you the progress of, oh, it's 13% of the way done with the study guide. And at the end of every run through the study guide, it's going to actually give itself a test on that validation data that it doesn't actually know the answers to. And so while this accuracy number here is helpful, because it's actually, okay, how good is it at remembering the study guide? This validation accuracy really is more important for us, because this tells us, well, how is it going to perform on new things? Anujan says, I've been following all your sessions via YouTube. The ML tracks are so detailed. I had only an idea of ML, but now I can say I work on Python to develop ML. That is so great. I'm so glad to hear that. That is actually like the dream case for this track, is you go from kind of not knowing too much and actually having a grasp on, like, I have created a model and kind of know what I'm doing here. So that is awesome to hear. That is sweet. And I'm totally covering up my face there. Let's see. We ran it with 10 epochs last time. Yeah. Okay, this is a question. Why does it take less time every time? This is a great question. Ooh, and we hit early stopping, which is cool. So why does it take less time every time? There are a couple answers that I would give for this, but the main one is, I think, going to come down to variability of our hardware. So I work on cloud, and this is a thing that we think about a lot, is the business of running a public cloud is having one giant chunk of hardware and then having to split it up among several different people that are asking you for a piece of it, right? What's so cool about Colab is that I don't have to own my own GPU and that I can still use one. But what that means is that I'm kind of sharing it with other people. And we try to be really clever about how we manage this sharing. But a lot of times that looks like if you haven't used it in a minute, we're going to clear all of your stuff out. And so this actually gets back to this idea of caching that we mentioned very briefly in our NumPy array session, where the idea of like, oh, if your stuff is located in memory close by, then it's going to be easy and fast to access. And I believe that would probably be the main thing that's going on here, especially because that first one was so long. There's almost this idea of like a warm-up period. Someone says it's like a starter threshold to clear it first. Yeah, I think once we signal, hey, we really want to use this GPU, and then it's like, okay, we're going to give you access to the GPU. That would be my guess, but these things can be pretty complex. I don't know if anybody else has any other theories there. In general, you would expect most of your epics to basically take the same amount of computational power. So great question. Okay, so we said early stopping here, and we set a patience of 3. And so basically, if you have multiple rounds where it doesn't seem like you're improving, then we would say, okay, like we can cut it off. You're not actually getting better. This additional time is not really helping you. And so we cut it off at epic 9. Even though we said you could do 20 epics, we only used 9 of them. So now I actually want to plot the history. We stored the output of this model fit session in a history variable, and we can use matplotlib to just plot this and see what it looks like. So we can say metrics equals history.history. So there's a history object that has a history object inside it, which contains our metrics. We'll say plt figure, fig size, and let's make it like pretty wide. So we'll say 10 by 5. And remember, we're just going to plot basically how did our model get better over time, or did it get better over time? So we can say plt plot, and on our x-axis, we can say history.epic. This will be the epics that we ran through. And then for the y values, we can say metrics loss and metrics val loss. So this is both how much loss there was on the data that it knew the answers to, and how much loss there was on the data it didn't know the answers to. And does anybody remember the difference between accuracy and loss? There are lots of good answers, and honestly, the explanation that I gave is like a little bit of a simplification. Anybody want to hazard a guess? No worries. Yeah, so this is a good contribution. Is accuracy is a measure of how well we're performing. If you have a higher accuracy, then you're performing better for sure. Oh, not plus y label, plot y label. Okay, so if we run this, it should show us our loss over time. Very cool. And then plt figure. We'll actually we can copy this and just edit it because we're going to do a pretty similar thing. And so now instead of saying loss, we can say accuracy. And then over here, we'll say validation accuracy. And oh yeah, we'll say epic and accuracy. We should get 2. Okay, yeah. So okay, we have lots of good contributions here. So one thing that we can just see very, very easily right off the bat, in fact, I'll zoom out a little bit here, is that, so this is our loss up here, and then over time loss goes down, and over time accuracy goes up. So they kind of have the sign flipped, right? If things get better, then your loss is low and your accuracy is high. So on some level, they're just kind of an inversion. And yeah, we have actually a lot of great sort of descriptions here. Loss is how far we are from the target. Accuracy is the number of correct predictions. And these are all basically right. So accuracy just purely is, you can think of on the test, if it's multiple choice and there are 100 questions and you get 90 of them correct, you have a 90% accuracy. And so it's a very sort of yes or no question of how many of them did you get just right, right? And that's really helpful because it gives you a really clear grade that you really know what that means. Like, out of all of the times you tried to give an answer, how many answers were correct? The reason this is not so helpful sometimes is that we can't nudge the model in the right direction if it's almost right. The sort of analogy that I would give here is on a math test, if you are doing a bunch of your work and you are really, really close to the right answer, but then you do one little error at the very end and so you get the wrong answer. Well, in terms of accuracy, you just didn't get it, right? You get 0 points in terms of accuracy. But if your teacher is trying to help you learn, then they might go through your work and see, oh, you're actually really, really close. You're pretty close to the right answer. And so I will give you some points and kind of nudge you in that direction. The sort of true thing here, or the more true thing here, is the idea that our model is really reporting probabilities. It's saying, well, I think it's really likely that this is the answer, but I think it's also likely this is the answer. And that is less bad than it being really, really certain of the wrong thing. This is maybe more in depth on loss and accuracy than we need to go, but the idea here is that loss is really better to learn from, whereas accuracy is better for reporting. Yeah, another good description of loss here. Okay, right on. So now let's actually look at our performance, and we can see that really quickly things kind of level off. So it looks like in both cases, blue is what we got on our training data, and then is this an orange color? The orange is what we got on data that we hadn't seen before. And so obviously you can see that we perform much better on data that we have seen than data that we haven't, which should be no surprise. But you can also see that pretty quickly we stop getting better, right? Really, honestly, by Epoch 2, we have made all of the gains in terms of validation performance that we're going to make. We actually keep improving on our training performance, right? We keep reducing our loss for training, and we keep reducing our loss, we keep increasing our accuracy for training. But for our validation stuff, we're not really getting better. That's an important thing to be aware of. So now I want to introduce, or really go back to this idea of convolutions. So in the last session, through a couple URLs of YouTube videos that I invited y'all to watch if you wanted to, but no pressure. And I'm going to see if I can find those again. Yes. Okay. So here we have a computer file video and a 3 blue, 1 brown video. And don't watch them now, but they're maybe, if you're interested in sort of the underlying math here, they're really helpful. So this idea of a convolution gets us around this problem of conspiracy theory brain. Conspiracy theory brain looks for connections everywhere, but a convolution is basically a sliding window that will only look at things right next to one another. And so we can introduce a layer of convolution, and basically it'll be a sliding window that goes over all of our input and just looks at how things local to each other really make sense of one another. And so you could have a window that actually is making sense of this S cluster, and then that window could slide over and make sense of this O cluster. And this might actually be a more robust way to get information that's useful to our model. Yeah, convolutions. The math is super interesting. The three blue, 1 brown video, I didn't remember how deep it goes into the math at the end. It does actually bring up Fourier transforms again, which is cool because we mentioned those 2 days ago. But really the first part there, just explaining this idea of this sliding window, is really helpful. I think we've actually used the convolutional neural nets in our natural language processing as well, because this is, okay, kind of a 2-dimensional sequence. But words are kind of a 1-dimensional sequence, right? You have one word right after the other, and having a convolutional window can often help you make sense of those as well. So, any questions about convolutions before we actually add one to our model? Sweet, then I guess we'll get going. And we know that about 50% accuracy over here is sort of our number to beat. If we can do better than that, then our learning and our introduction of a convolution is going to be worthwhile. So I'm going to copy our code for our simple model. And actually, I'm going to say, let's introduce a text blocks and say more convoluted model. But I'm going to put convoluted in italics so you know that I'm making a very funny joke. Okay, so we have our simple model, but let's replace simple with CNN for convolutional neural network. So we can start at the same. We can use the same input shape. But what we want to do, I'm jumping between different note stocks here. Okay, yes. But what we want to do is introduce a convolutional layer. Now, convolutional layers, just like all our other layers, we can kind of think of them as Lego blocks. We don't actually have to do the math for them. And so what we might do is, before we flatten, once we flatten, sort of all of our positional information is gone, right? Remember, flattening just gives you a giant list of numbers. And so we want to do anything where we actually care about the order of our data, we want to do that before. So we can take our input shape. We could maybe do some resizing. So we could say layers dot resizing 32, 32. This is just going to resize your data into different dimensions for you. And then we can say layers dot conv2d as opposed to a one-dimensional convolution. So we actually have a two-dimensional window that's sliding around. And then we can actually pick the size of our window and how far the window will move every step. So we could say this window is going to be 32. The window. Or sorry, no. We're first going to say the number of different filters we can use, or the number of different windows we can use. And then we can pick the actual size of our kernel, so to speak. So the kernel is that sort of the size of the window that's sliding around. And we could, if we wanted to, we could stack two of these, which maybe we'll try this just like this first, and then we can add more afterwards. It will filter data. Yeah, sort of. I mean, so one of the ideas that we threw out is that the core concept of machine learning is you have data in the form, or experience in the form of data that you give to a giant ball of math, and that giant ball of math gives you predictions, right? And we were kind of in the process now of breaking down, well, when we say that giant ball of math, what are we talking about? And all of these sort of layers are different balls of math that we can introduce into our sort of Frankenstein AI brain. And so a dense layer is sort of a conspiracy theory brain, and a convolutional two-dimensional layer is sort of like an artist that sort of scans a piece of art, kind of scans back and forth, and looks for connections of things that are close to one another. Something that we will all often use when we have a multiple convolutional filters is something called a pooling layer. So I'm trying to decide how deep I want to go on specifically on this topic. I love how due to maybe Will having more screens on the left, Blahaj is more visible. Yeah, I really try to put my important stuff over here, so I'm constantly looking here. Okay, so we will talk about this for just a few minutes. So we talked about how we have these different filters that our convolutional layer is going to be running across our input image, basically, right? We can think of our spectrogram as an image. And each of those filters, in theory, is going to accomplish something different. So it's not actually crazy to think of a filter that's just going to go around just looking for S's. It's going to look at this spectrogram, and it's going to know that whenever you have an S, it's going to look vaguely like this. It might not be the exact same shape or the exact same size, but it'll have roughly that kind of contour to it. And you might have another filter that's just going to look for plosives, right? We figured out that our plosives are kind of these vertical lines here because so this is a stop spectrogram, or a spectrogram of the word stop. And so we actually can see the t sound right here and a p sound. And both of those are plosives, and they tend to take up a wide range of frequency space, and they're pretty short, right? So you could have a filter that is just looking for plosives. And so what we actually want to do is we want to give our model the ability to make multiple filters that can accomplish different things. In sort of classic image processing, you'll think of some of your filters might be edge detectors. So you have filters that'll go around and just look for, is there an edge right here? And we might have filters that end up being, oh, is an S right here? Or is this a vowel? And I want to put a fine point on the fact that I'm saying we could have filters like this, but we don't have to pick any of these things. We just have to set the parameter of how many filters do you get. And our model will do the work of figuring out, well, what should this filter be? And what should this other filter be? I know we're getting a little bit into the realm of theory with our convolutional filters. So ask questions if you have them, but don't think you have to understand everything about the math here in order to use it. So that's what our convolutional layer is doing, and it hopefully will pick up lots of different kinds of patterns. Incredible. Oh, right. Okay. So the reason that we talked about that is because the next layer we're going to add is something called a max pooling layer. So when you have all these different filters, like one of them might be, is there an S right here? And another one might be, is there a T right here? And another one might be, is there silence over here? And because we have all those filters, they actually end up in a stack. So if we want to, we could actually get a summary. We could say CNN model summary. And this might actually fail to compile. Oh, no, it does. Okay, it's fine. But so you can see that right on our input, after resizing, is just a 32 by 32, basically a grid. But then when we run our convolution, it actually becomes 32 30 by 30 grids. This is what I was kind of talking about when we spent time thinking about the shape of different matrices and how it becomes kind of important. So there are two parts of this. One is that because our filter size is 3, as it's sliding across our image, it's actually going to end up cutting off parts of it because you don't want to run the filter sort of half hanging out, right? And so you end up cutting off the very edges of your image as you're running the filter across it. And so we go down from 32 to 30 and 32 to 30. But then because we have 32 different filters running through, we end up with 32 copies of this 30 by 30 image. So we have just now like radically changed the shape of our data from one image to 32 copies of the image that are all picking up on different things, right? Like one of them will be picking up on, is there a T? And another one will be picking up on, is there a vowel sound here, or something like that. And so in order to actually collapse that all together, we will often use something called a max pooling layer. So we could say layers.maxPooling 2D. And all this is going to do is it's going to lay all of our copies of this image on top of each other and look for where basically the brightest points are. So you can imagine like right here, that if you laid a bunch of copies of this image on top, there would still be things that would certainly pop out. You'd still have things like right here that pop out because that's such kind of a high contrast moment there. And that is our convolutional layer. I'm going to sort of re-emphasize that if you are not getting the underlying mechanisms of all these layers, that's okay. That kind of comes with time. But knowing that you can sort of plug these layers in and play around with them, I think is really powerful. So now let's run this again and look at our shapes. And we get 15 by 15 by 32, which is not exactly what I thought we would get. Let me think about that for a second. I'm going to come back to why that is our shape and why the pooling brought down the size. Oh, right. It's the dimension that it's operating on is not the sort of temporal dimension. It's the sort of X and Y dimension. It's grouping things. It's doing the max pooling on things that are themselves locally close. Hopefully that scans and makes sense. So we have a new model now. We've added a convolutional layer and a pooling layer, and then we're flattening it and just feeding it through our dense network. And if we want to, we can compile this and give it a whirl. So we can say CNN model compile. And really, actually, we could just borrow the same compilation step from up here. We compiled our simple model, and we can compile our convolutional model in just the same way. Remember, the optimizer just tells our model how to do some fancy math. Our loss is the sort of grading grading with respect to how much work you put in and can kind of give you partial credit. And accuracy is our metric that just says, well, how many of them did you get right? So we can now write another training loop, and we can say history equals CNN model dot fit. Fig. Fit. And we can say train spec ds. And we can say validation data is equal to our val spec data set. And we can pick our number of epochs. And let's say we give the other one 20. Let's give this one 20 as well. And let's let her rip, I suppose, and see what happens. And maybe while we do this, we can set up the next thing because it'll take a minute to run. So this will run our convolutions. Ooh, okay, this is actually a fun, to me, a fun detail. So it looks like it is, yeah, I should have a training soundtrack that makes it all dramatic. So these were taking, it started at like 25 seconds, then got down to basically stable 9 seconds per epoch there. And down here, we're seeing similar. The first one ran a little bit long, but then we're coming down here. And one of the reasons you might think, well, hey, we added extra steps. Why is this not taking longer? And it is actually taking, it looks like maybe on average, just a tiny bit longer. The other one was averaging, it looks like 8 or 9 seconds. And this one is more like 9 or 10. But something that is cool about convolutional neural networks is that they have they're really easy to parallelize. And the word parallelize, I know, is a tricky one that kind of twists your tongue. But when we talk about can a model be parallelized, we're really talking about can we break it up into small parts and run them all at the same time. So when you have to run a model basically sequentially, it means that if you have lots of steps, it's going to take longer. But if you run a model in parallel, then you can actually speed it up by sending different computations that you need to do to different parts, different parts of the GPU. They can be spread apart, or multiple processors if you have multiple processors. And so a thing that once you get sort of deep into machine learning, a really, really nice property for your model to have is being able to be parallelized. This is actually one of the the big developments with, if you are read up on sort of the current state-of-the-art research, we're really into transformer models, and they are a big improvement over sort of our sequence models, like our LSTMs. And one of the reasons is that transformers are just really, really easy to parallelize. And that's like a big deal. How come we did not do patience again for this run? That is a great question. Mostly, I just didn't put it in there. We could. I actually kind of am interested in how this sort of evolves over time, and I don't want to cut it off early. Honestly, part of it is actually for the first one, we knew we weren't actually going to use that long term. Although it might have been interesting to run the other one without the early stopping as well. It's something that you can play around if you want to. I would totally support that. Okay, so we're getting some great results, or at least some interesting ones, right? So we see that our accuracy on stuff that we have seen is getting really quite high. We're getting to like 86%, 87%. And then parallel. Are you counting the number of times that I say parallelize? And then we can see that our validation score is we're doing better. We're doing better than we did with our sort of simpler model, but it's not kicking butt. It's doing fine. We seem to be topping out around here. 13. That's good. Somebody clip it and do a Twitch clip. And there we are. Okay. I'm going to grab our graphing code. So we can grab our graphing snippet here and run that down here as well, because I want to see how this evolves over time as well. And oh my goodness, this is so great. This is so interesting. So our accuracy basically bottoms out at around, we could actually just go up and look, but like 66, 65%. So we're getting about 66 or 65% of them correct. And as we talked about the other day, because we have 8 options, 1 divided by 8 is the percentage we'd expect to get right if we were just randomly guessing. And 1 divided by 8 is like 12.5%. So we're doing way better than random guessing, right? We're actually doing really, really quite good compared to random guessing. But we're not doing perfect, right? We're not doing gangbusters. And one of the reasons, this is why it's really helpful to plot both your loss and your sort of final metric like accuracy, is because we're actually getting worse on loss. Our loss is actually going up after a bit. And we're not really getting questions wrong, but we seem to be drifting away from the truth. And one of the reasons this can be due to, it's something that I think I bring up almost every Global Hack Week, is this idea of overfitting. It is the question of, is your model starting to learn patterns that aren't really there? And if you see your model get worse when you give it extra time to train, that might be a sign that your model is starting to learn patterns that don't actually matter, which really gets us back to this idea of conspiracy brain, right? Is it picking up on things that are not quite there? And so one thing that we'll often do if we're trying to fight overfitting or conspiracy brain is something called dropout. Now, dropout is something that you can add to pretty much any model, but really what it means is just make things a little bit noisy for your model. I think if I was going to try to bring it back to our analogy with the study guide, you know how sometimes, I don't know if you had any teachers that did this, but I had math teachers that would give you a study guide and they'd have certain questions, right? Or my physics teacher did this a lot. He'd give you a study guide that had different questions and you could study them. And then he'd use the same question on the test, but he would use different numbers, right? He would just change it up just a little bit. Just so if you had memorized the answer, well, this question, it's not going to look exactly like the question on the study guide. It might be sort of in ways that matter, basically the same, if you learned what you were supposed to learn. But if you were just memorizing the exact words, he messed it up a little bit. He changed something here or there, so you would actually get tripped up if you were just trying to memorize things. And this is basically what dropout is. It says at this layer, just fuzz things up a little bit. So the general idea is still the same, but if you tried to memorize, it wouldn't work out for you. And so I think we're gonna add dropout, and then we're gonna take a break, and we're going to announce some raffle winners, and that's what we're gonna do. Okay, sweet. So to add dropout, again, this idea of Legos that we can play with our model, we can say layers dot dropout, and all you have to give this is a number, which is sort of the percent of fuzziness you want. And so we can give it a percentage of 0.25, or the rate, as of how many different things are you obscuring as you pass it along. And often when you have sort of more complex layers, you don't want to add dropout sort of in the middle of them. So this sort of, we can think of this convolutional layer followed by max pooling. Because max pooling isn't actually learning anything, it doesn't really benefit us to put dropout like between those two things. But in between our dense layer here and our convolutional layer, we could add a little bit of dropout, and that would maybe be helpful. And we could also, if we wanted to, add some dropout after our dense layer. So we have 2 dense layers here that, remember, are both the ones that are searching for conspiracy theories and looking at for any connection. And so if we add some dropout in between those, we might think that it could be, we could reduce some of this overfitting we get near the end. Oh yeah, Samred called it overfitting. I'm so glad that the example made sense to folks. So we can run this, and remember, so we'll compile it and let it rip. And it looks like maybe we can add the early stopping back. I don't think it was hurting us at all. We can add it to our fitting step. And so what we're looking for is really this curve. We just don't want this curve to be as steep or go up as far, right? We don't want it to, if it spends more time thinking about it, like become less confident in its answers. So that would be, if this step is actually helpful for us, we would hope for that loss, that sort of overfitting loss creep, to go down or to not go up as highly. So we'll let it run. We should expect to see roughly a similar pattern to how high it can get. Although you'll often see when you add this sort of guard against overfitting, it may take longer, and you might actually not get quite as high a training accuracy. So I actually kind of wish I had copied the old training log so we could compare. But you might actually, I guess we have the graphs here. So you might actually expect this blue accuracy to not actually go up as fast. In theory, you should still be able to basically hit the same heights of accuracy, but it might take a little bit longer to get there. Let's see, Barrett asked, I think I missed it, but what's the difference between loss and val loss? Same for accuracy as well. Yes, great question. So in blue, we have how did it perform on the data that it already knew the answers to. So this is basically the study guide where we gave it the questions and the answers. How often did it get it right? And then I think it's like an orange line. I don't know, I'm colorblind. But this is basically how well did it perform on things that it hasn't seen before. So a test that it has never actually seen the answers to, how well does it perform? And so what we see is it studies the study guide, and it keeps getting better at the study guide, right? Its accuracy in the study guide keeps going up, but its accuracy on the validation or the test that it doesn't know the answers to yet, that bottoms out or tops out at about 66%. Yeah, exactly. Loss on trading data and val loss on unseen validation data. And it looks like we stopped at 61% validation accuracy. So, okay, I'm going to actually run this separately. I really should just save these images somewhere, but we'll just create a bunch of cells. I don't know why it's not just running. Why is this taking you a long time? This shouldn't take a long time. I'm suspicious. Y'all, if our kernel crashes, I will be very sad. Okay, let's try it again. Okay, sweet. Okay, cool. So what we see is roughly what we expected. The big win here is that the distance between our accuracy or our test accuracy, our train accuracy and our validation accuracy has gotten smaller, right? It's no longer really, really confident about stuff where it knows the answers and not confident about stuff it hasn't seen. It's roughly similar levels of confident about both of them. These things are more correlated. And we don't have this huge creep up of validation loss. It doesn't start getting less confident in its correct answers as it's given more time. So this is roughly, I think, a win. Okay, I think that we're gonna pause just for a second. We're gonna do one more edit to our model when we come back, but I think that I want to announce raffle, I guess. So this is for folks that don't remember, everybody who submitted feedback in the feedback forms. I have, first of all, really appreciated the feedback. It has helped me guide how fast I'm moving and what I answer in more depth, and that has been great. And of course, you voted for the two things that are on my cheeks right now. But also, that is how I'm running the raffle, is if you submitted all three of the previous ones, then I took all of the emails that submitted all three of them into a spreadsheet, and then I randomized range, and then I took the top three of in that range. And those are the individuals that will be getting swag drops. I actually have already sent those names to Mary, and she was like, hell yes, let's give these folks some swag, which is great. And now I'm looking for where I left this spreadsheet. But let's get a chat drum roll, please. And honestly, I wish I could give literally everyone a swag drop because y'all are the core squad. And I really appreciate that you're here. Okay, and actually, I actually know these people's names, so I don't have to read out their full emails. Raffle winner number one. Oh, thank you so much for the drums. Raffle number one is Stuart Fong. Everybody give Stuart a round of a hand for winning the raffle. Raffle winner number two is Akib. Everybody give Akib a round of applause for winning the raffle. And then finally, raffle winner number 3 this is one where the email does not match the username, but winner number 3 is Polar Void. So give Polar Void a round of applause for winning the raffle. I also want to shout out everybody who did not win, but did all 3 sessions or all of the 3 previous sessions. And I'm having trouble because I don't want to out anybody's email on stream. That would be inappropriate. But some of them I don't actually know the connection to. The one that I do see is Andrew Fancy Appleby did all 3. So shout out to Fancy Appleby. I really appreciate that, hacker. And the other ones, Sanchit, I think, was on stream. I remember that person. Pummy, shout out to Pummy if they're there. And yeah. Oh, Mo, yeah, okay. Mo, email starts with believer. Right on. Well, thank you so much for everybody who's attended these sessions. You're incredible. You're all very near and dear to my heart. And we'll get some swag to some folks. And if you didn't win this time, I think I will do the exact same thing next time. So pull through. I will say there were only 1, 2, 3, 4, 5, 6, 7, 8, 9 individuals that did all 3. And so you had a 1 in 3 chance of winning. So the odds are not actually that bad. But right on. So let's get back to hacking. And any questions about adding our dropout there? We're adding sort of this little bit of noise, and that is making it so that our brain does not learn quite as many conspiracy theories, which we really love, right? And we're still not, we're doing good on accuracy, right? We're doing way better than random guessing, but we'd still like to give our model a little bit more power. And so something that we can consider adding is another layer of convolution. We'll do this a lot in image networks, where we will actually have sometimes 4 or 5 or 6 layers of convolution. And the way that with images this works is that you are really building up higher and more abstract features. So an example that we'll use is, maybe your first layer of convolution is just edge detection, right? And it's just or basic shape detection. Is this a curve, or is it a vertical line or a horizontal line, right? And then maybe your next layer can actually pick up on some very rudimentary shapes, right? Like, is this sort of an oblong shape? Is this a spike? Is this a triangle? And then above that, you might have a layer that can capture things like actual features in real life. Like maybe if you're looking at cats and dogs, maybe something could be a whisker, or something else could be an ear. And then at the very top level, you get this very high level feature like, is it a cat or a dog, right? And so you can actually think about this in our spectrogram, like what are the different layers of sort of abstraction here? And obviously we have sort of our individual cells, right? But we, know that we picked out these shapes of, well, this is actually an S shape. That's what a S sound looks like. This is what a T sound looks like, right? But then we also know that the combination of these different shapes together actually does make different words, right? That a stop is like all those individual things put together. And so this is not a super rigorous way of doing machine learning, but it's actually something that happens quite a bit, is you think about, well, what patterns might I want my network to pick up on? And so how can I give it the capacity to do that? So if we come down right after our layer of convolution here, we could add another layer that looks basically the same. And so this would give it another chance to sort of do things to see patterns that are localized. Another thing is I just realized we're not using our normalization layer. So remember that our norm layer basically just makes everything the same volume. So normalization sort of takes the really loud things and brings them down, and takes the really quiet things and brings them up. Because we don't want to just be good at loud data or just be good at quiet data. And so by normalizing the volume, this will make everything similar. And this looks different because we actually defined this up above. If we scroll all the way up, where did we do it? Okay, yeah, we built our normalization layer here. So we can add that. We can add this additional convolution. And I want to give this a try. And let's see what this will do for us. We can compile. Let's actually just we could grab this and just store it in a comment. Let's see. Or we can store it as text, I guess. That's a lot of output. Actually, that's more output than we really need. Wait, how did I select all this? This is a disaster. I just want to copy this right here. Okay. And we can label this as one layer of convolution. Did that explanation of sort of these different levels of features building up kind of make sense to folks, where first you might just detect shapes or edges, and then you might detect, more complex things. At the very top level, you're trying to actually identify, well, is this whole thing a cat or a dog? And, oh no, this was supposed to be text. It shouldn't run. Oh, there's our text box. Okay, so pretty bad formatting, but it's there. Okay, so now we can actually train our new model that we just compiled that has 2 layers of convolution, and it normalizes. And a thing that we're kind of balancing here is, as we give it more power, we actually are giving it a greater ability to come up with conspiracy theories. We're giving it a better, more power to just try to memorize answers if it wants to. And so that's something that we're kind of balancing that against the adding dropout and making things fuzzy and trying to prevent overfitting. So we want to give it all the power, but we want to try to stop our model from using that power for evil, basically. So it's like building up levels of confidence till it arrives at an accurate conclusion. Yeah, I think this would not be a terrible way of framing it. I think this at least makes sense to me. Okay, cool. We see we're getting up to 62% validation accuracy. Another thing that's great here is you can see right here, our accuracy and our validation accuracy are almost identical. Which is something that you really, really like to see as a machine learning engineer. We keep going, and okay, it ends up still getting a little bit better at the training data than it does at the validation data. And on some level, that might just be inevitable. But we are slowly but surely climbing up. You see, we had a step where we fell back down. We went from 64 to 63, but then the next time we went back up to 65. I really am trying to get my like exciting event announcer, or like providing color commentary to watching a model train, which honestly is not an easy job, but I live to inject a little drama into our neural network training itself. Okay, we hit early stopping again. And this time we got to 65-ish%. And we can graph this again. We could maybe... I guess we can get rid of this first one so we can rerun this. And cool. So these actually look fairly similar. Here it looks like we're topping out at about 60%, but up here we're topping out like a little bit closer to 65 in terms of accuracy. Lucky number 10 for early ending. Yeah, it's a good point. I'm now kind of interested in like trying it without the early stopping, but I'll leave it for now. And so this is maybe the place that we'll leave this current iteration of the model is, okay, we're getting about 2/3 of these correct, and we are also what was I going to say? We're about 2/3 of them correct, and we're not having huge deviations from our training data and our testing data, which is radical. So now something that I want to introduce is the idea of a confusion matrix. So we're going to use our validation data and actually dive into not just how many predictions does it get correct, but what do the predictions kind of look like? What does it tend to do well on, and what does it tend to do poorly on? So we could say, first we're going to actually generate some predictions. So if you just want to actually do a one-off predict some stuff model, we can send cnnModel.predict, and we can pass in our val spec ds, and we can call that y predictions. And let's look at the predictions that it's spitting out. And this is actually going to be, I think, a good learning experience in and of its own right. Okay, what is this? Giant chunk of numbers. This this may be a little bit confusing to you. It's like, why are these our predictions? It's supposed to give us a class, right? It's supposed to say, well, is it up, down, left, right, stop, go, etc. And it's not giving us that. It's giving us these really kind of like long tail numbers. And the answer is that these are probabilities. It is saying, well, I think it is most probable or least probable that something is, this class is the right answer. And technically it's not strict probabilities, but more negative numbers are low probabilities and really high numbers are really high probabilities. So you have to kind of squint and do the math for scientific notation. But like this first one here, if we took the first, we should be able to take the first row. Perfect. So here's our first row. And so this is actually probabilities with heavy air quotes for each of our classes. If we pull out our, I think we called them label names, it's saying, okay, there's comparatively low, but not no chance of it being down. There's a really low chance of it being go. There is, again, a low, but not nothing chance of it being left. There's a really low chance of it being no. There's actually a decent chance of it being right, an even higher chance of it being stop, and the highest chance of it being up. And then finally, there's a really low chance of it being yes. And so if we were actually to say, well, what thing did it actually guess? We would say, well, it probably guessed that it is, 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. We'd guess that it is guessing up. That's basically what it's saying has the highest probability. So how do we turn this list of probabilities into, or relative probabilities, into an actual label? And the answer is with this very nifty function called argmax that I think I'm just going to show you how it works separately, because it's a really, really useful function that comes up again and again. So say we had an array, we could say my array is equal to np.array, and it'll be two-dimensional. And let's say, actually, the example we're gonna use is this is question, or it's a multiple choice question, and this is your guesses for each of the options. So we have A, B, C, and D. And what this matrix in here is going to represent is how likely did you think that each answer was. So what if we were like really confident that on question number 1, the right answer was A? So you might say there's a 90% chance that it's A, there's a 5% chance that it's B, there's a 0% chance that it's C, and a 5% chance that it's D, right? And then on the second question, maybe we're actually not quite as certain. And so maybe we think it's probably B. Oh, maybe we think it's probably B, but B we give like a 50% chance, and then A we give a 25% chance, and C we give a 25% chance, and D we give a 0% chance. So this is basically us just saying how confident are we in each of these answers, right? And so if we wanted to actually go from this guesses of probabilities to, well, what answer did you actually pick? We can use something called argmax, which we can say tf argmax, and pass in my array. And what it's going to basically do is say, well, what was the index for the maximum value in each of these rows? We can say axis 1, which basically says find the maximum on the dimension number 1, which would be the columns. And we'll see our answers here are 0 and 1. So the 0th thing, or A, had the highest probability in this first row. And then the 1th index, or B, had the highest probability in the second row. Any questions about argmax? It's a thing that actually pops up a lot when you're doing stuff with TensorFlow, with NumPy. So I actually felt like it's worth mentioning. So we can actually run tf.argmax on our entire set of predictions. Remember, our original set of predictions is just a list of these sets of different probabilities. And so we can say tf argmax of y prediction. We can say axis equals 1. And we can say y, we could just reassign this to y predictions. So we're replacing our y predictions with actually the class name or the class index. And so now if we look at the first thing in ypred, it says NumPy 6. So it's just saying, oh yeah, it's the 6th thing, which for us was up. Sweet. So now we're going to get our sort of true values, or the actual correct values. And so the expression we're going to use, it's a little bit syntactic-y, but we can say tf concat list of val spec ds dot map. Remember, mapping, we can just use this to apply some function to everything in our data set. And we'll use a lambda here. And we're going to get in both our, in this we're going to get both in our audio and our label. And we just want to return just our label. So all this is doing is just pulling out our label for us. And then we can say axis 0, so we can group these all together into a similar matrix. And we can call this y true. And if we did this right, then we should be able to look at y true, and it should just be a list of numbers. And something that's actually pretty exciting, if you remember from up here, we can actually go through and look at the ones that we got correct, right? Because these are our predictions, and this is the truth. And it's like, okay, we guessed 6 for the first thing, and it was 6. We guessed 7 for the second thing, and it actually was 7. So we can actually see our wins here. So we mentioned a confusion matrix earlier in the session, and I want to mention sort of what that is, but it's kind of easier to talk about when you can actually see one. And so we're just going to code it up really quickly. We're going to import Seaborn as SNS. This is just another graphing library that makes heat maps really, really cute. And we'll call our confusion matrix. We will create this with tf.math confusion matrix, really aptly named. And we will pass it both our truth and our predictions. We'll just create a matplotlib figure, fig size. We'll do 10 by 8. And now we can do sns.heatmap and pass in our confusion matrix from up here. We'll actually want labels on here, so we'll say xtick labels equals label names, and ytick labels equals label names. And we'll want to annotate that. And we can say our x label is predictions. Just kind of bear with me here and trust that this will look cool and we'll be able to talk about it. Usually I like to explain it before we actually do the thing, but this is one where once you see the visual, I think it makes a lot more sense. And if we did everything right here, boom, behold the beauty. I'm actually very into this visualization. So this is a heat map, meaning that things that are sort of this warmer color or this lighter color are higher numbers. And deep down here, the dark end is low numbers. But what we're actually looking at here, and you might have to get in close to see this, is on the left, we have the label of what things were actually, like for any given sound sample, what the correct label was. And then down here, we have what the prediction was. So for example, if we go down right here and down right here, there were 132 samples that really were down and that we labeled down correctly, right? But of the samples that really were supposed to be labeled down, we labeled 19 of them as go. So there was a little bit of confusion between those two things, between down and go. But if we look between down and left, there was only one sample that was supposed to be labeled down that we labeled left. And that actually maybe makes a little bit of sense that, oh, down and go both have like some deep O sounds, but down and left are like just really, really different, right? Mo says, this is so smart. Now we can study where our model messed up. Yeah, exactly. This is like giving our, this is a great comment, this is giving our student of our model like really detailed feedback of what it needs to improve on, right? And this is pretty cool. Now, why would you look at this? There are a lot of reasons, and usually why you look at a confusion matrix depends on your problem space. So, for example, say we were building a model that was going to give people loans, right? And we wanted to give people who were going to pay back the loans, we wanted to give them loans, and people who wouldn't be able to pay back the loans, we don't want to give them the loans, right? This is like sort of a classic example. Well, this is a case where it's not, so the problem isn't symmetrical, right? You would actually much prefer to not, if you're the bank, right? Which I'm not making any broad statement about the morality of finance, but if you're a bank, you would prefer to have 100% of the loans that you give out get paid back, right? And you actually don't care as much if you don't give out a loan to somebody that could pay it back. You just want to make sure that nobody that you give it to won't pay it back, right? And this is, I think Samred mentioned false positives and false negatives, and this is exactly that, where you don't actually care about different kinds of wrongness the same, right? Another classic example of this is in testing for medical conditions. So if you're going to test someone for cancer, it's really, really bad if they have cancer and you miss it. But if they don't have cancer and you say, it looks like you might have cancer, well, then you go and you order another test and you find out, right? And that's actually not that bad. It's still a hassle. It's still not great. But if you could prioritize telling some people, hey, you should get more tests done, over telling somebody who has cancer, yeah, you're fine, dude. You would prefer the former. And so this is kind of the point of looking at something like this. Let's see. Brit says no and no, a lower number, 61, because of the confusion with the existence of go. Yeah, this is a really, really interesting question. So of things that are supposed to be labeled no, 61 of them got labeled as no, but then it looks like a lot of them got labeled as down and go. And this is, I think, super, super interesting. And we mentioned like why we might be interested in this kind of data set, but I want to actually ground this. Say you are talking to a self-driving car, right? And it recognizes a couple of these commands, like left, down, go, etc. Well, there are actually some things that we care about like quite a bit. If you say go and the car maybe stalls and you have to say go again, that's not that bad. But if the car asks, hey, do you want me to crash into this pedestrian? And you say no, and it actually acknowledges that you said go, that's like really, really bad, right? We want you to be able to say no to your robot and for the robot to understand that like really all the time. And so this is something that we actually really care about. So I think our last crowning achievement here, Polar Void said I'd be scared if somebody told me that. I assume this is about cancer, which yes, it's not to say that there's no downside to telling somebody who is healthy that they have cancer, but it's just that there's a lower downside than missing something. Because in that case, all you have to deal with is some hassle as opposed to dealing with like dying of cancer, We actually might not care about all these outcomes equally, and in this scenario, we want to make sure that, probably stop and no are probably the two most important words here. Thankfully, stop actually does pretty well. Stop, we mostly get it correct. But with no, especially the fact that it gets confused with go, this really, really becomes a problem for us. So one of the tools that we have in our toolbox is when you don't care about all of the outcomes exactly equally, you can actually use something called class weights. And basically, this is going to give your model sort of preferential treatment on the questions that you think are really, really important, right? So, this is like if you're in medical school and there's a unit on like doing plastic surgery to make your clients look pretty, and there's a unit on like not giving your clients or your patients, not clients, not giving your patients opioids. It's like, okay, that second session is like way more important, right? We want to really make sure you get those questions correct. And so we can introduce something called class weights. And I think this would be the last thing that we do, but I believe this is something that we can actually just pass into our training loop. So in order to actually build our class weight dictionary, which I believe is what we actually pass in, let's see, actually, let's just look it up. Giving class weights to Keras. Define a dictionary with your labels and associated weights and add it in as class weight. Boom, perfect. So we want to build a dictionary of weights for how important are each of these answers. And we can do that. I mean, we can do that down here. It's fine. So we'll have our label names. And actually, let's get our actual indices as well. So we can say, let's see, list, enumerate, label names. So enumerate is just going to give us the numbers along with them, so what their index is, which will just be easy for us. And then we can build a class weights dictionary with each of these. So, okay, we have 0, we have 1, 2, 3, etc. And we can say, how important is this? And so we picked that no and stop are probably the most important things, right? So we could give no and stop ratings of, I don't know, 100, right? Really, really high. So let's say 0 down is not that important. Let's give it a rating of, maybe we go 25, or we do 1 to 4. So everything that's not important gets a 1, and everything that's really important, we give a 4. And this is just, we're kind of playing around. Go, we'll also give it a 1. Left, not left. 2, we'll give it a 1. 3, because that's no, we'll give that a 4. Right, we'll give a 1. Stop, which is 5, we'll give that a 4 as well, because stopping is really important. 6 is up, we'll give that a 1. Oh, wait, yeah. Colons. And yes, 7 will also give a 1. We could probably build this dictionary in a more elegant way, but let's just build it like that. And so this is a way of saying the things that are really important are labels 3 and 5, which are no and stop, which for obvious reasons are important. Even trained models can sort of understand consent. Yeah, this is basically, I think is a good way of putting it. This is us telling our model, hey, if somebody tells you no, you really, really need to respect that. Do you confirm your purchase of $69,000 on Amazon? No, purchase confirmed. This I feel like, as we can really get into the world of dark patterns in machine learning, is yeah, you could trick people into buying stuff if you want to, which would be bad, and you shouldn't do it, to be clear. Okay, cool. So we built our class weight, and I'll just actually copy things down here so we can get them fresh. So we can recompile our model. Recompile a fresh model. Take a second. And then we can run fit on it. And I believe we just pass class weights equals class weight, or class weight equals class weight. And let's see what this does. Let's see if it yells at us. Let's see, Brit said, for something like directions for a self-driving car, I can imagine each aspect will be extremely and equally important. How does the machine learning react to that? Yeah, so this is a good point. In our sort of toy example here, I am saying, hey, like we're going to preferentially say stopping is stopping and saying no are more important. And I actually feel like pretty good about that. But obviously, if you have a self-driving car, you can't be like you couldn't say if 63% of the trips you go on you don't crash. Like no one would buy that car, right? And so obviously there is this. Well, we want all of our models just to be better all the time, and there are different thresholds for just is a model safe depending on what it's doing. But then within that, assuming that we have some sort of range of well, this is the performance we can get. You can make trade-offs about what things you're going to prioritize. So I think really the thing that I would say for a self-driving car is the other dimension here is you can just go out and get more data. And with self-driving cars, I mean, we're working from, I think, 10,000 examples here. With a self-driving car, you probably want like millions of hours of driving data. And of those millions of hours of driving data, each of those hours is probably like trillions of images of different things and what the car did next. And so so I think that if you actually just need higher performance, like if that's just really, really important, then oftentimes the answer is you got to go get more data. I would still say, even then, it's like I would want the most. Oh, thank you, Mo. Even then, I would say probably the most important thing a car can do is like if you say like turn on the brakes, it should brake. I would still say that's more important than a lot of other things because actually that does fix a lot of other problems if the car is misbehaving. But yeah, with that, it's like you just need it to be performant all around. It's a good question. So thank you for asking. Okay, cool. So we actually stopped really quick here, but. Oh, actually, we shouldn't have just compiled. Well, this is, we can see what happens. This is interesting. Okay, right on. So let's, just because I'm curious, regraph our performance. And so I believe we were actually starting from our previously trained model, which actually I'll fix that. Let's just rebuild our model to start with. So if we rerun actually defining the model, then we should actually be able to come down here and recompile and then fit, which will again take some time. And then we can plot our history. And then what I'm really interested in is getting that confusion matrix again and seeing if we are no longer making the same kinds of mistakes, right? In fact, we might actually make more mistakes, but the mistakes that we make might be mistakes that we're more okay with, right? If it occasionally when you want it to go left goes right, maybe that's better than when you say no, it's saying, okay, I'm going to go and do it. And in fact, I mean, obviously too early to say, but it looks like we are improving a little bit more slowly. Yeah, building on the last model. So yeah, so if you actually see what happened here is we started with our old model. You can run multiple fit sessions on the same model. And that's what we did here is we said, okay, take that model that we just trained and then now start training it with these new priorities, basically. And that's, I mean, sometimes that can actually be really, really helpful. A lot of really interesting machine learning science involves different training steps. Sometimes when you freeze different parts of the model. But we just kind of want to get a clean take on if we say, hey, you're really, really not allowed to mess up the word no and the word stop. Okay, we aren't really stopping. And this is actually, I think helpful from an illustrative purpose. I mean, one really interesting our lines are really close together, which I think is perhaps a function of the fact that we are just telling it to so highly prioritize these two cases, which is I think interesting. But now the moment of truth, let's regenerate our predictions. So we'll have to run prediction again. This is just going to be me copying a lot of commands. Run prediction. We'll get those actual labels from prediction. We will get our true values. run that. And then we will graph our confusion matrix again. And let's see what happens. Okay, cool. This is great. This is actually exactly what we were hoping for. So what we see is that a lot of things did actually get worse, right? And we're now actually accidentally classifying a lot of other things as no, but it is very, very rare that something actually was no, and we ended up classifying it as something that wasn't no. And the same goes for stop, right? If it's stop, you are almost certainly going to predict that it's stop. There are a lot of other things you might predict that are stop as well, but you are not going to, or it's very, very unlikely that you're going to mess up the example stop when you see it. And so this is something that I think is, I actually love making this a feature in this Global Hack Week, is that you have to make trade-offs in machine learning, and oftentimes those trade-offs are between overall model performance and like real things that you care about, right? And I think that having more machine learning engineers that are actually interested in weighing the, okay, I'm doing all of my fancy math here, but like this thing is probably going to affect real people, and like what do those real people care about and what would be good for them? That holding both of those things in your head as you are building models that affect people's lives is really, really valuable. And so in this scenario, we really are making a sort of overall performance for safety trade-off. And obviously, if we were building a self-driving car, we would just need the performance to be way better across the board. But in this scenario, in this sort of toy case, I think that making this overall performance for safety trade-off really makes a lot of sense. Another place where this kind of thought process will come up is when it comes to discrimination. In our example of offering loans to folks, like one thing that you could actually go and look at is, are we more likely to offer folks loans if they are white than if they are brown? And you don't want to do that because that's racist. And so you actually might have to go in and tweak your model and say, hey, like something that you really shouldn't do is not offer someone a loan just because they're not white, right? That's like a thing that you would actually think about implementing into your model. And one of the ways that you could do that is actually from a very crude perspective of assigning a class weight. This is actually not exactly the path that I expected this stream to go on, but there is a book called, I believe it's called Ethical Algorithms. The Ethical Algorithm, yeah. And I love this book. I think it's a really, really great survey of different, mostly machine learning things, but lots of different computer science. And it is maybe the thing that I'll leave you with, every day I've left you with some different YouTube video, but maybe the thing that I will leave you with today is The Ethical Algorithm by Aaron Roth and Michael Kearns. Oh, and it looks like there's a PDF version of it. Okay. Is this actually the full book? Oh, this is not the full book. The Ethical Algorithm by Michael Kearns and Aaron Roth. I'm not going to send the Amazon link because they're not paying me to do that, but I'll just pass the title of the book there. Now it's going to be impossible to get in your car in the morning. Yeah, it's going to be impossible to get into a self-driving car, at least for a hot minute. I'm actually currently studying to get my pilot's license, and it's something that I feel a lot about. Once going through the training of realizing all the ways that things can go wrong, it's like even when I'm going to get on a plane this Saturday, and it's like, it's going to be tough for me to get on that plane knowing like all the ways that planes can crash now. Yeah, I should really make this work for me and get paid when y'all buy The Ethical Algorithm from Jeff Bezos. Good deal. So I think that's where we're going to leave this. I just got on my soapbox and we talked about ethical algorithms, which is just great, which is more than I had hoped for this session. I think the last thing to do is to drop the feedback link. Two last things is to drop the feedback link so y'all can let me know how this session went and what you'd be interested in doing next time. I can honestly say this whole Global Hack Week track is based on, I think, 2 different people that asked for audio stuff from last time. And so if you want to pick what we do next time, like let me know in this form. I will drop the link in the chat. Additionally, because y'all are, again, the core squad, giving me any feedback on how I've been explaining things or other things you want to learn about, or even just how your experience has been, that would be great. Of course, letting me know sort of speed and enjoyability. And then I suppose, also I'm asking you in this form what I should let y'all vote on next time. We have done dyeing my hair and tattooing my arm and painting on my face. So I need additional ideas. And the last thing is someone asked to see more art. And so there are 2 pieces of art that I will show off today. I don't have the phone to go and be mobile, but I do have both pieces of art back here. One is actually one that I created. Y'all know that I have been getting into Japanese woodblock carving prints. And so I have done another one. First, I'll show you the woodblocks. So this was a bit of a smaller work. I only had 3 different layers. So here was our key block. And then we have a sky block. And then we have a sort of water and mountain block. And I decided to do this one all in grayscale because I kind of am enjoying playing with value these days. And so the final product is right here. There you go. Boom. The working title, I don't have an actual title and I haven't signed them, but the working title here is Archipelago. So I'm trying to get better at composition and the idea of like creating depth in a space and sort of having, having things get smaller as they move away and interesting placements. So there's art piece number 1 for you. Thank you so much. I actually enjoy showing off art because it's fun to get feedback, especially when it's positive. Well, thank you all very, very much. I'll cycle through people saying nice things because I like that. Let's see. Polar Void said, ooh. Anodjan said, could you do one more bonus session on ML where you provide us with a summary of it? That is something that I will absolutely consider doing next time. I actually don't. We plan these things relatively far in advance, and so I don't actually even know if I asked Mary if I could do another one, if there would be like a slot for it. Apparently, we actually do get scheduled up pretty fully. Okay, last piece of art. I guess only the second piece of art, but here we go. Next time we use ML to teach our PCs to make art. I mean, that could be a fun session. And so this was one that I just recently acquired for the collection. We talked a little bit about my like collecting proclivities, and there's this one artist, Hasui Kawase, or Kawase Hasui, depending on which order you put the names in. And he was active sort of in the early half of the 20th century and did a lot of these really, really stunning sort of landscape compositions. And he's part of the Shin Hanga movement. Anyway, I just acquired a new Lifetime Edition Hasui. And, there's a little bit of glare, which absolutely we cannot have. So I'll lean back a little bit. And so there is the Hasui. And I feel like because of the nature of streaming, I have to actually leave it there for like multiple minutes so that an actual clear image will come through. But I'll just hang out. So yeah, beautiful, beautiful composition of a little shrine above a lake. Really into the reflection in the water. In general, just very into it. So yeah, there's the art tour. This I'm probably going to frame and put in my bedroom. And I don't know, I kind of like the idea of every Global Hack Week just showing you the update on the art collection. Isn't that reflection pretty cool? I'm really, and that's something that I'm trying to get better at in my own art, is being able to do sort of realistic reflections. Yes, yeah, there's a lot of Hasui art that kind of gives sort of a Studio Ghibli aesthetic, which actually, to be fair, there is like a artistic tradition that you can pull through. Katsushika Hokusai, who did like the Great Wave that we've talked about before, he actually, the other main thing that he did is he actually carved blocks for manga. In the, I think it was like the late, oh gosh, don't quote me on this. When was Hokusai active? He was born in 1760. I was going to say the late 1700s. Active. Okay, yeah, so really kind of the early 18th or the early 1800s. But so he did these beautiful works of art, and he also did manga. He like carved wood blocks to print manga, and so there's like an interesting web of connection between these different art forms, which I think is dope. And I think that's where we're gonna leave it. I will hang out for just a second to monitor chat in case anybody has any burning questions. Let me know if you want to admit you got a crush on me before 2023. And then I think we will see each other again in the new year after we all have, hopefully, a very restful holiday season. So thank you so much for being here. I'm going to drop that final feedback link again. Honestly, this final feedback link is the one that I care the most about because it is the folks that have actually done the entire session with me. So please let me know your thoughts on that one. I really, really read them, and they are super useful for planning future things. And happy hacking and happy Global Hack Week, and you're all brilliant. And Merry Christmas, happy holidays, joyous Kwanzaa, etc., etc. Everybody take care of yourselves. I will see you next Global Hack Week.